Good morning, Amherst Chem students. Today is Wednesday, the 18th of March, 2020. As we get into the distance learning mode, I'm starting to get questions coming back. That's good. Keep them coming. Email me, message me, contact me through Google Classroom, whichever way, but keep the information coming back and forth. I'm operating in a vacuum here, so I need your feedback. Today we're going to turn our attention to worksheet 4, which focuses on Table G. This is it's a fairly difficult worksheet, so you're probably going to want to rewind this video a lot, and there is clearly not enough space to work with these the amount of space between the lines. So it's a work in progress. Most of these worksheets, as we get into the year, they're all works in progress. We'll get there. So if you get Table G, a calculator, and some separate paper, and worksheet 4, we'll work through a few of these together, and I'll post a key later today. Some of it's straightforward, some of it is not. First thing you need to know is that when you're looking at Table G, the guidelines for Regents is that they'll accept answers that are plus or minus 1/3 of a grid space. That might be a little over generous if you ask me. I mean, the grid space here is worth 10. You're going to be plus or minus 3 in reading one of these things. I doubt they'd accept that much, but that's their rule of thumb, plus or minus 1/3 of a grid space. All right, so first thing you need to know, it's got a horrible title. It should be Solubility as a function of temperature, y as a function of x, always. So what we've got going on here are a number of lines. When you look at solubility, it's a part to part. So this is grams of solute per 100 grams of solvent, water, as a function of temperature, which we know is average kinetic energy of the particles of a substance. One of the things you'll notice is that solids tend to have a positive slope, whereas gases tend to have a negative slope. In terms of kinetic molecular theory, why would that be true? Well, here's a solid in a regular geometric pattern called a crystal lattice, with not much ability to move other than to vibrate back and forth. As you increase temperature, particles want to move more. I mean, average kinetic energy is energy of motion. So if a solid goes into the aqueous state, it gains the ability to rotate and translate in between the water molecules. More ability to move. So there's incentive for a solid to dissolve. But if you're a gas and you're dissolved, and you increase the temperature even more, there is incentive to get away from the water molecules and to go into the gas phase. So as you increase in temperature, particles want to move more. Solids can move more if they're dissolved. Gases can move more if they're not dissolved. So solids become more soluble as temperature increases. Gases become less soluble as temperature increases. I want to focus here briefly on this per 100 grams of water. There are a number of questions you'll see which are based on different amounts of water. And even on the Regents exams you'll see this. It's just a simple proportion. So let's go to the worksheet briefly. Which salt has its solubility least affected by changes in temperature? Who's got the flattest slope? For my money, that's NaCl. Its slope really stays consistent at about 38 and 39 and maxes out at about 40 grams of NaCl per 100 grams of water. Which solute is most affected by changes in temperature? Who's got the steepest slope? Potassium nitrate, KNO3, good old saltpeter. Okay, it's almost vertical at points. I mean, that's ridiculous. If we were in lab, we would do a solubility experiment based on KNO3. We would take some, heat it up until it all dissolves, cool it down until it precipitates out, and we would make our own little Table G and it's actually quite accurate for KNO3. For substances on Table G, state the trend in solubility. We said solids increase as temperature goes up, gases decrease. Which substances, so as temperature increases, solubility increases. That's true for solids. As temperature increases, solubility decreases. For gases, which substance decrease? On our chart, it would be SO2, NH3, and HCl. And those are indeed all gases at STP. So HCl, NH3, SO2. Those are the gases. So hydrochloric acid, ammonia, and SO2, the smell of burnt matches. In terms of kinetic molecular theory, why? We just talked about that. As temperature increases, particles want to move more. Solids can move more if they're dissolved. Gases can move more if they're not dissolved. I'll let you fill that out. Let's focus here on these three questions, and then I'm going to turn you loose on the rest of the worksheet. And some of these they're quite challenging, so devote a little time to this one today. How many grams of KNO3 can be dissolved into 100 grams of water at 40 degrees C? Here's 40 degrees C. Here's the line for KNO3. Here's 100 grams of water. You say, well, bingo, that's about 64. What if I had 50 grams of water? Same temperature. Well, if I can fit 64 grams into 100 grams of water, what would it be into 50? Half as much. 32. What if I had 200 grams of water? If it's 64 into 100, it's going to be twice as much. 128 into 200. So it's just a proportion. It's also important that you pay attention to all these questions that they're always talking about. How much water? Otherwise, you're going to do a lot of work for a problem and find out that you had to scale it up or scale it down. 100 grams of water, 100 grams of water, 200 grams of water there, 200 there, 500 there. Okay, there are a couple where you need to look out for that. All right, I'll let you guys work on those. Some of these problems in here, you're going to need more space for sure. But let's talk about supersaturation. I had the video with the beaker full of water and sugar, and I saturated it. And that's a good starting point. If you're below the line on Table G for solubility as a function of temperature, we said you're unsaturated here. If you're on the line, you're saturated, and if you're above the line, you're in supersaturated. I'm going to search YouTube for some videos because we had an awesome lab on supersaturation. It's just fun, it's cool to do. I'm hoping there's something out there which at least gives you an idea of what it looks like. But how do you make a supersaturated solution? What's up with that? I mean, we know that if we took a beaker with some water in it, we put in some solute, and it all dissolves, you can't see it anymore, we were unsaturated. But if I keep adding more solute, keep adding more solute, keep adding more solute, eventually I'm going to get to a point where there's excess at the bottom of the beaker. And the solution above here would be saturated. It can't hold anymore. That's actually an equilibrium, which is part of our next unit, but it looks like nothing's happening, but the rate of dissolving and the rate of precipitating are equal to each other. The net change turns out to be 0. 1 in, 1 out. So this solution's concentration remains constant. Every time a crystal dissolves, another crystal comes out. So how do you get into this supersaturated range? Well, if I take at room temperature roughly 20 degrees C, and I make a saturated solution, like I have here, with excess solute in the bottom. And I heat it up. Let's take it up to almost 100 degrees Celsius. We'll put it into a bath of boiling water. All of that excess solute is going to dissolve. So here I am at 20. I've got excess solute. I heat it up to 100, and I'm going to be under the curve. It's all going to dissolve. I'm unsaturated. So here I am, saturated. Here I am, unsaturated. Now, not all solutes will do this, but if you're really careful about it and you have really clean glassware and you don't go too fast, if I allow this solution to cool it, man, just cool it, I can actually cross this line. Most substances, when you hit this line, they precipitate out. That's what our lab with KNO3 did. But if I used sodium sulfate or sodium acetate and my glassware was clean, I can get this curve to cool all the way down, even to 0 degrees C. So if I were to take this and put it in an ice water bath, and just let it sit there surrounded by ice water, it stays without precipitate. I'm here. I'm down near 0 degrees Celsius. I shouldn't have been able to hold that much. I couldn't hold it at 20. Why should I be able to hold that much dissolved solute at 0? That situation is a supersaturated solution. It's unstable. It's not going to stay there. The minute you add one small crystal to quote-unquote seed the precipitation process, all of the excess will come out, and you'll see this crystal start to form, and it looks like it's freezing. It's actually exothermic. It actually releases heat, but for the solutes we use, but it looks like it's freezing. It's not. All of the excess solute comes out. All of this extra stuff comes out, and it goes back down, creates a slurry, which if you were to stir it around, all that excess solute goes back down to the bottom. You're left with another saturated solution and excess down here. I'll find a video. I'll post a video of somebody doing that because I'm sure it's online. So how do you make a supersaturated solution? You make a saturated solution at room temperature. You heat it up, make it unsaturated. You very carefully cool it. Cool it, man. Carefully. And if it doesn't precipitate, it's supersaturated. You want to get it back down to saturation? Add a seed crystal. It'll precipitate out. If ever you've seen those little heat packets with the little clicker in them, you know, you get a little plastic kind of packet. You're supposed to throw them in boiling water, and it all dissolves, and it's got a little piece of aluminum there, and you click it. That helps create the seed crystal, and they look like they're freezing, but they actually get warm. Yeah, that's sodium acetate. If you cracked it open, it smells like vinegar, because vinegar is acetic acid. You may have seen these before. They're kind of cool. All right, so I'm going to post a link to a supersaturated solution experiment, and I'm going to post answers to Table G, worksheet 4, which is, I'll warn you, there are some doozies in there. It's a fairly tough worksheet, so ask me questions. I need the feedback. I need to know how you're doing. Talk soon.